Okay, good evening. Only Stevenson is there, right? We'll wait for some more time. What happened, people? Only still two of you. It's almost 5:10. Uh, okay, fine. I'll be back in a moment. Okay, so give me one. Okay, fine, people. So even though we have two people, will continue because we already know we are little tight with the schedule. Okay, fine. So maybe if only two of you, then maybe I'll finish in 1 hour. I'll not take till 6:30. Okay, unless and until people join. Okay, so we'll see what we can do. Right. Okay. Right. So yeah, as I said, we'll be starting with redox reactions, right? So in this chapter, we'll be seeing about how to calculate the oxidation number, which you already know about, but I'm going to tell you some special cases, right? And then we'll be seeing about how to balance the redox reactions, right? So these two are the major parts. I would say. Now, obviously, the last part is going to deal with what is that? Yeah. So the last part is going to deal with the hardness of water, right? And I'm going to tell you about something regarding to H2O, not H2O, H2O2, hydrogen peroxide. Okay, so that's something called as volume strength of hydrogen peroxide that we'll see. Right. Okay. So we already know what is oxidation, what is reduction. I don't have to tell you what is it. So anyways, if you have to sum it up. So oxidation is a process where I add oxygen or remove hydrogen, right? Or if in terms of electrons, I can say that if some species loses electron, that is what is going to be oxidation. And you know what is oxidation number? So I can tell you this also. Whenever I have increase in oxidation number, that is going to be oxidation. And then going to reduction, addition of hydrogen, or removal of oxygen, or addition of electrons, right? And lastly, when I go for oxidation number, I'm really sorry about the background noise. Okay, I think it will be fine in a while. There is something going on. Okay. Right. Okay. So yeah, what I was telling. Right, guys. Okay. So reduction, right? Reduction will be addition of hydrogen or removal of oxygen or addition of electron, or in terms of oxidation number, it is going to be decrease in oxidation number. Right. Okay. So we already know all this, right? So we'll directly go for what do you mean by oxidation number and how to calculate it. Again, you know most of it are going to be special cases. And before that, I want to tell you one thing. So remember, right? So if someone tells you this is an oxidation reaction, there is some reaction, okay, and they tell you that this is an oxidation reaction, or say someone tells you that that particular reaction is a reduction reaction, actually it's not going to be like that. Okay, so if you see properly, right, you will see that there cannot be a reaction where only oxidation happens, or say only reduction happens. This is not possible. Okay, if at all oxidation happens, reduction has to happen in the reaction. Say if one of the species gets oxidized, right, the other species has to get reduced. Say for example, if you look into this reaction, say if I have carbon plus oxygen giving carbon dioxide, right? So generally they say that this is going to be oxidation reaction, because you see that carbon is two carbon I have added oxygen, right? But if you look at what is happening to oxygen, oxygen is actually getting reduced. Okay, so any reaction for that matter, if you're going to take, right, so there cannot be a reaction where oxidation can happen independently or reduction can happen independently. It is always going to be a redox reaction, right? Both oxidation and reduction will happen simultaneously if it happens, right? Okay, so that is about one thing. Yeah, so what I was telling, yes, that's about oxidation and reduction. Okay, so anyways, we'll directly move on to oxidation number. Okay, sorry, oxidation number, right? So oxidation number, if how will I define it, right? So it's defined as the actual charge possessed by that particular element in a compound, as simple as that. It is the charge possessed by the element in a particular compound. Again, some elements can have different oxidations in the different elements, right? But again, as simple as it is the charge possessed by the particular element in a compound. Okay, right. Now, there are certain standard values of oxidation number for certain elements. Okay, say for example, first if you take hydrogen, right? Say hydrogen can either have +1 or -1 depending on to which element is attached to. Right? Obviously, you will understand that if you find that the hydrogen atom is attached to a highly electronegative element like oxygen or fluorine or any other electronegative element, you will see that hydrogen is going to have +1. Right? And whenever you see hydrogen atom is attached with what is that? Hydrogen atom is attached with highly electropositive elements like hydride, sodium hydride, that hydride, lithium aluminum hydride, all these things. In those cases, you will see that hydrogen element is going to have -1 oxidation state, right? Okay, and it can even have 0. Please remember one thing about oxidation number. If you find that the elements are in their free states, right, their oxidation numbers are 0. Please remember this. For example, if I ask you what is the oxidation number of hydrogen in H2, 0. What is the oxidation number of O2? I mean, oxygen in O2, 0. What is the oxidation number of sodium element? 0. Right? So when you know how the elements are going to exist in their standard states and how they are available in nature, in what form they're available in nature, those particular times you will say that obviously the oxidation numbers of those elements are 0. Magnesium solid, 0. Zinc solid, 0. Chlorine gas, 0. Right? So whenever you see elements in their standard states or free states, how they are available in nature, for them the oxidation number is 0. Okay, so fine. So the first is about hydrogen. Next is about oxygen. Right? Now oxygen can have actually -2, -1, -half, and +2. All these oxidation states are possible. Right? This is obviously, I know, is a common thing. Oxide, normal oxides, whatever you have, sodium oxide, magnesium oxide, carbon dioxide, water, all these things are normal oxides, right? So in all these cases, you'll see that the oxidation number of oxygen will be -2, right? Okay. Now -1 is for peroxides. right? So whenever you have a O single bond linkage, right? Actually, I should write it as O2 2 minus. That is how I represented a peroxide anion, right? O2 2 minus, O single bond with a minus minus on both oxygen atoms, right? So in that case, you will see that the oxygen is going to have -1 as a charge. So hydrogen peroxide, if you take there, the oxidation number of oxygen is -1, right? So you have something called as peroxy acids, right? So even you can have in your people of you have studied, right? Peroxy acid. So many sulfur. In sulfur, I can have a peroxy acid. With phosphorus, I can have a peroxy acid. So whenever you have a peroxy acid, for those oxygen atoms which are having the O linkage alone, right? Those cases you will see that oxygen is going to have -1, right? So this is for peroxide. And minus half is again minus half and +2 are going to be very rare, right? +2 is going to be only in one compound. I'll tell you what is that. So in this case, minus half is going to be for superoxides, right? Say superoxides will be formed by generally group 1 elements, right? Group 1 elements are going to be potassium, sodium, those elements, lithium, sodium, potassium, right? Say one of the superoxides can be KO2, right? So KO2 or K2, KO2, right? So you'll see that here is going to be -1/2 if you check, right? So you know how to calculate it. Maybe it's this is +1. So you'll see that oxygen is going to have -1/2. I'll tell you how. Anyways, right? In this case, superoxides, I'm going to have -1/2 as the oxidation number for oxygen. Okay. And lastly, +2 will happen only in one compound, and that compound will be OF2, right? So whenever you see oxygen forming compound with fluorine, right, this is the only compound possible. Okay, so in those cases, I can actually there are two. I even have +1 also. I have O2F2. Two compounds are possible with oxygen and fluorine. Obviously, I know fluorine is more electronegative than oxygen, so fluorine should have -1. There is no other. Fluorine can have only -1. There is no other possibility for your fluorine, right? But oxygen being the most next most electronegative element, mostly you will see only negative oxidation states. But if at all you see that it is going to bond with fluorine, then you can have, say, in this case it's going to be +2. In case of O2F2, it's going to be +1. Okay, so yeah, that is about oxygen atoms, right? Now, then I can sell certain things like for sure, like if I'm going to have group 1 elements, they will always have +1 charge only. There's no other possibility, right? So lithium, sodium, potassium, rubidium, cesium, you will not see any other oxidation state. Only +1 is possible. No other state is possible. Okay, so same way I can say that group 2 is going to have +2, but again, we'll not go into details. If you want, you can write that group 2 elements will always have +2. Okay, fine. Now, when I go for fluorine alone, as I told you, fluorine will always have only -1 as the uh, -1 as the oxidation number. Okay, no other thing is possible. Okay, so these are all some constant things you have to know, right? Other than that, you have to calculate it. Okay, other than this, you really have to calculate the oxidation numbers. Okay, so we'll just take one example, right? Because you should have been doing it in your coordination compounds, right? But anyways, we'll just do it here. For example, if I have H2SO4, right, and I want to know what is the oxidation number of sulfur here, right? So remember, if you add up the individual charges possessed by the elements here, that should be equal to the overall charge, right? Now, obviously, in case of a compound, always the overall charge is going to be 0, correct? So obviously, when you have a compound, you sum up all the oxidation numbers of all these elements, and then you equate it to 0. But if at all, if it's a cation or an anion, right, then you have to equate it to the whatever the amount of charge it is there. For example, if total charge is +1, then you equate it to +1. Say if I just remove this and I put SO42 minus, right? So in this case, you have to add the oxidation numbers of sulfur and oxygen along with the number of oxygen atoms. Please remember, right? Now that has to be made equal to the overall charge. In this case, would be -2, right? So if you calculate, say if I take H2SO4 only, right? So you will see that for hydrogen it is +1, right? Because it is attached with more electronegative elements. So there are 2 hydrogen atoms having +1. I don't know what is the oxidation number for sulfur, and I have 4 oxygen atoms each having -2, and the overall charge will be 0. So you'll see that sulfur is going to be in +6 oxidation state. Okay, pretty easy, right? Fine. Now, if at all I have to take some little not so easy cases, okay. Say for example, if you have NH4 NO3 ammonium nitrate salt. Okay. Now, if I ask you, what is the oxidation state of this nitrogen here? Can you just calculate and tell me? Nitrogen's oxidation number. I still hope only two of you are. Minus?
-1.
-1. Okay, fine. So generally, I know what you would have done. You would have just returned it as N2H4O3, right? So this is how you could have written it. So 2x plus 4 minus 6 is 0. So yeah, x will be equal to +1, right? This will become -2. Yeah, +1. Right. Okay. But this is really not right. Okay. This is absolutely wrong. Right. Now, in these kind of things, what you have to understand is these are two different ions. One is NH4 plus ion. The other one is NO3 minus ion. Okay. So you cannot calculate it like this. Right. So in this particular case, nitrogen is even though nitrogen is going to be there there are two nitrogen atoms, but these two nitrogen atoms are going to have two different oxidation states. Okay, and whatever your value you are getting here when you calculate like this, that is the average oxidation state. Let me prove it to you. Okay, say now in this case NH4 plus, if I have to calculate what is the oxidation number of nitrogen, right? What will you do? You will put x plus 5 equal to +1. So you'll put x as -4, right? So in this case, nitrogen is having -4, right? So let me calculate the nitrate ion. X minus 6 is -1. So x will be +5. Okay, right. So now these two are the two different oxidation states. -4 and +5 are the oxidation states of nitrogen and ammonium nitrate. Right. Now you take the average of these two. Say if you take average 5 minus 4, am I doing correct? Yeah. So 5 minus
-3.
Where is it -3?
Instead of -4, it's minus.
Yeah, correct. It's 4, right? So it's -3. Absolutely. So 5 minus 3 divided by 2, because there are two nitrogen atoms, right? So now what will you get is 1. That's what you're getting here. Okay, so like this, I can give you more examples. If I have, say, Fe3O4, it's called ferrosulfuric oxide. Okay, so Fe3O4, if you try to calculate, right? So just try and calculate and see what you're getting.
8/3, sir.
Correct. You see, obviously, at least in this case, it's pretty difficult to understand that you might have went wrong because you're getting a whole number. But in these cases, whenever you see there is a fractional oxidation state, please understand that it is really not possible. How can I have a fractional charge? Right? Really not possible. That means obviously there is something wrong. So how will you write this compound? Is actually it's a mix. These are what are called as mixed oxides. Okay, so mixed oxides are going to be a combination of two different oxides. Say one of them is FeO, the other one is Fe2O3. So if you just add up these two, you'll be ending up with Fe2. Okay, so again, what you see here is there are going to be two different oxidation states for iron here. And if you just see what are there are going to be 3 iron atoms, 2 of them are going to have one value, and obviously because it's this compound, and one of the iron atom is going to have this value. Then if you take the average, then you will end up with 8/3. Right? Okay. So if you do it, obviously I can understand that here it's going to be +2 for Fe, right? And here if you calculate, here it's going to be +3 for Fe. Right, so this +2 and +3 are the oxidation states of iron in Fe3O4. Right, now if you take the average, what will you do? 2 plus 3 into 2, that is basically there are 2 iron atoms having +3, right, and one iron atom having +2, divided by 3, you will get it as 8/3. So again, you see That is the average oxidation number, and that is really not the real value. Okay, real value is like this. Okay, so I even have a PbO and PbO2. If I do it, what am I going to get? Pb2O3. So again, Pb2O3, if you calculate, again you will end up with fractional oxidation states. Will you get fractional oxidation states? Yeah, you will not get fractional oxidation states, but you have to understand that the only two oxides possible are PbO and PbO2. So Pbe2O3 is a mixed oxide. Again, you will have two different oxidation states here. Okay, fine. So these are all some extra things, and obviously, if I also have one special compound, right? So that special compound is this CrO5 molecule. Okay. Now, if you just take what is the oxidation number for chromium here, what will you get? You will get chromium as +10, right? So again, +10. See, remember, maximum oxidation state possible is +8, right? And that is given only by two elements in the entire periodic table. One is osmium, and the other one I forgot. Oh my god, that is also a D block element. Okay, osmium. So I hope you remember osmium tetroxide. So in this case, osmium is going to have +8 oxidation state. Okay, let me see if you remember. Where do I use osmium tetroxide in organic chemistry? Where do I use osmium tetroxide?
For alcohols, sir.
Okay. So what is the reagent to which you will add, or the substrate to which you add the OSO4, and you will be ending up with, yeah, it is alcohol.
Alkenes.
Okay, good. So if I have an alkene and if I add OSO4, so you will be getting a diol. Okay, both the double bonds will go, the pi bond will break. The carbon atoms having the double bond will have one OH and another OH, right? And I told you there is some speciality about this. What is speciality of OSO4? If the diols, what kind of diols you'll get?
Vicinal.
That's obvious. Vicinal, yeah, obviously vicinal diols. The next carbon atoms are going to have, but you have to understand that it is going to be syn addition, right? Both the OH will be on the same side. It's not like one OH will be pointing down, the other OH will be pointing up. That is called anti-addition, right? But whenever you go for this OSO4, or when you go for KMNO4, both these cases you will see that the OH is going to add in a syn way, syn addition, same side. Nice, right? So that is organic. So anyway, so you see, what I'm trying to tell you here is the maximum oxidation state possible is +8. Now, anything more than that is unrealistic. For osmium, for +8 itself, I should remove 8 electrons from this, and that is really not going to happen because it's not an ionic compound, right? So it's just a way of looking at it. It's a covalent compound, so obviously it's not like it has lost 8 electrons. No. Right. So anyways, so that means +10 is never going to be a possibility. CrO5 is really not going to be what is that? Going to have +10 oxidation state. Right. So now we are going to delve into oxidation numbers calculation by looking at the structure of the molecule. Okay. So for most of them, for simple compounds, you'll be able to easily find or calculate the oxidation states. But for certain compounds, right, it is not only for certain compounds, actually for every compound it's actually good that you draw the structure and then you decide the oxidation number. That actually will be helpful, right? But again, you'll see, if you can understand what is the structure here, right, then you will really understand why is it not going to be +10. Okay, fine. So if you look at it, chromium, one, wait.
Sir, is it CrO3 2 minus and
No.
O2, sir?
No. That is this is not a mixed oxide, not a big deal. See, this is the structure. Okay,
Oh,
so
okay,
this is
sir.
the structure for CrO5. Okay. Now what
Yes,
you
sir.
see is that this oxygen atom is no problem. This oxygen atom is normal oxygen. That this is going to have -2 oxygen. Okay. But if you look at these 4 oxygen atoms, now you see there is a OO single bond linkage. OO single bond linkage. So it is not a normal oxide. It's actually a peroxide. Okay. So all these oxygen atoms are actually going to have -1, -1, -1, -1. Right now you can easily see what will be the oxidation state: -2, -3, -4, -5, -6. So obviously this chromium should have had +6 as the oxidation state. Okay, so this particular structure is what is called as butterfly structure because it somehow resembles butterfly. Correct, right? So this is, in this case, you see that it is going to have +6 oxidation state. Okay, so there are a lot of things like this. Let me actually, I'm looking for a textbook which has so many structures like this. Just give me a moment, people. I'll bring the structures for you. Just give me a moment. Okay. Okay, so when I have, say, for example, H2SO5, okay, H2SO5, right? So again, if you calculate, you are going to get some number, right? So you will give, maybe if you just calculate it, you can even do it. So 2 for hydrogen, X for sulfur, and -10 for oxygen. So you'll see that this is going to be +8, right? So again, sulfur, right? Maximum oxidation state possible, right? Maximum oxidation state possible for sulfur is +6 because it has 6 valence electrons. I really cannot remove any electron which is not in the valence shell. Remember that, right? Sulfur has 6 valence electrons, so maximum I can do is going to be 6 electrons I can remove. So +6 will be the oxidation state. But what you see here is, again, it's going to be +8, but again there is going to be a problem, right? So for this, again, you have to know the structure of this molecule, right? So this is what is called as Caro's acid. Right, this is just extra information. If you want, you can remember. So sulfur, how many over? 1, 2, 3, 4. There is one more oxygen. Am I doing it correctly? Oh, there is one more, right? Sorry. Okay, done. Right, fine. Now you look at it, right? There are actually 2 oxygen atoms that are having -2. Actually, 3 oxygen atoms having -2, right? And one of the oxygen atom is not even attached to this, but these 2 oxygen atoms are actually going to have -1 and -1, and obviously the hydrogen atoms are going to have +1 and +1. There is no doubt, right? So when again you see that there is a peroxide linkage here. Okay, so obviously we know peroxide linkage, oxygen is going to have -1 as the oxidation state, right? So now if you calculate, there are 3 oxygen atoms having -2, 2 oxygen atoms having -1, and obviously hydrogen atoms having +1. So if you do that, it will be 2 + 2 for hydrogen, sulfur I don't know, and 3 of the oxygen atom is having -2, 1, 2, 3, and +2 of the oxygen atom is having -1, and the overall charge is 0. So now if you calculate, it will be -6, -8, -8 + 2 will become +6. Yeah, that turns out to be.
Sir,
Yeah.
So how can the oxygen attached to the left of sulfur have -2 as the charge?
Oh, this one.
Yes, sir.
Easy, right? So you see, whenever you see oxygen, like see, for example, I can even tell like this then. Now, how is it going to be -2 here? So whenever you see oxygen single bond alone, at that time alone, there is going to be a problem. I'm going to have -1. But generally, oxygen will have two bonds. Okay, so it doesn't matter what other two elements are going to be there. As long as oxygen atom is going to have two bonds, it is going to have -1, except that when you see one of the bond is going to be O single bond, then only it is -1. Okay.
Yes, sir. Yes, sir.
Right. Cool. So that's about H2SO5. I can give you one more like this. Say if I take this is a very nice example, right? I'll just take S4O6 2 minus, right? S4O6 2 minus, right? So see, there are only few things like this, right? So if you can just remember all these structures, it will be really helpful. But again, questions whether it's gonna come or not, very less chances. Okay, so anyways, so if you just look at the structure of this molecule, again, whatever you're going to calculate, that is going to be completely wrong, right? So remember, whenever you are going to have especially sulfur and oxygen compounds, right, please make sure that you are going to have the structure with you. If not, you will not be able to answer the questions of oxidation numbers. Okay, right, fine. Now, if I look at the structure here, S4O62 minus, now you are going to have, say, 1 O minus, other sulfur atom is going to have 1 O minus. Done. Minus 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 2 is done. Right. Now you have how much you have accounted for? You accounted for 6 oxygen atoms also, 1, 2, 3, 1, 2, 3, 6 oxygen atoms also accounted for. Right. Now the only way you will be able to do this is if you attach sulfur atoms. Okay, now this is the only possible structure. You can come up with any other structure you want, but electronically or structurally, it will not be correct. Right? Say you can tell me, sir, maybe if I can draw another structure, something if I have to draw, say, not possible. Right? Say something I have to bring in. One, two, three, four, five, 6. But again, you're not able to account for the negative charges minus minus, right? Or I actually, if it's like this, maybe you're able to account for it. But if you look at the what is the charge, this is -2, -2, -1, and it's +5 for this. And again, +5 is not a suitable number, right? +5 for sulfur is not a suitable number. But anyways, guys, you don't have to go for trial and error. It's better that you just understand, you remember the structure. That's always going to be more. That's going to be pretty easier thing rather than to predict the structure. Remember the structure. Certain times in chemistry, you have to remember things, right? Fine. So now, please look at this. So if we just concentrate on these two sulfur atoms, right? Now these two sulfur atoms, can't you see that it's like S double bond S? Is it not? This is attached to sulfur. This is attached to another sulfur. So this particular sulfur it attached to two other sulfur. Again, this particular sulfur is attached to two other sulfur atoms, right? So obviously, what you can understand is this particular can be the analog, or say this can be the derived structure of this particular sulfur atoms. And obviously, we know this is how sulfur exists in nature. Not exactly as S2, but still S8. But still, you whenever you have SS bond, you don't have actually like per how should I? It's peroxide per sulfide. Actually, you don't have something called as per sulfide bonds. I've never heard of it, at least. Okay, so there's nothing like that. Okay, so now for these two sulfur atoms, for the oxidation number is 0 because they're almost like they're existing in their natural states, right? Okay, Now, if you go for these or these things, but again, I'm going to get +5. Am I? Okay, fine. Let me check. What am I going to get? Right. Say this is -2, -2, -1. Again, I'm going to get +5. Oh, but that shouldn't be correct. Correct. Oh, but oxidation number 2, sulfur atom to oxygen atom is +5. Yeah, guys, this is actually +5 only, to my surprise. Okay, so even in that structure, right, you are actually you are getting only +5, right? But this is the correct structure. Okay, so the questions can be like this, right? With the set of oxidation numbers for all the four sulfur atoms in this particular molecule, they'll give you have to choose the option as 5, 0, right? If you just put as 5 and 5, no, or say something like some other option is going to be wrong. So that's the reason. Okay, so you have to understand that here 2 of the sulfur atom is going to be in 0 oxidation state, only for peculiar molecules like this. Okay, you don't have to remember much. One last thing, and then we're going to wind up with this. Okay, right, and that last thing is S2O3 2 minus. Okay, S2O3 2 minus, and I'll directly give you the structure for that. S2O3 2 minus. So the structure is going to look like this. Okay, right, so you see again, this is -2, -2, -1. So this sulfur atom is going to have +5, right, and this sulfur atom is going to have -1. Easily I can say that. Okay, again, whenever you see SS bond, that you don't actually take into account for a electron transfer. Okay, so oxygen, this is -2, -2, this is minus what? But how is this -1? Oh, okay, correct one. Fine. So this is -1, -2, -2. So +5. This is -1. Okay, right. Fine. So that is about the peculiar types of compounds where you have to remember the structure for you to answer the oxidation number question. Okay. Other than that, there's nothing. Okay. Remember, at least for S4O6 and S2O3, remember the structures. Then you will be able to easily remember the oxidation numbers. Right. Okay. Fine. Next. Moving on. Now we'll move on to see how do you balance an oxidation reaction, balance a redox reaction. Right. Now there are going to be two methods, right? But we will see only one of them because this is not your school that they will ask you, solve this by this method. No. All you have to do is just get the answer. Right. Okay. So right. So now fine. So we are going to see balancing. Right, so only one method I'm going to teach you. I'm not going to teach you the other method because I don't want to get confused. The method which I'm going to teach is half reaction method, and this is the best. There are other reactions called oxidation number method, but here also I'm going to use oxidation number only, but a little different way. Okay, so the first one is a half reaction method, and this is going to be a little less confusing. Whatever the type of reaction, you know, hope you know what is called as a disproportionation reaction, conproportionation reaction. Now those kind of reactions, solving it through the other method is a little confusing, but here it's going to be crystal clear. You are not going to face any problems, right? Okay, so now what I'll do is let me take some examples. No, actually I have to give you the rules first, right? So now the rules, first one is that obviously I have to write the reaction, the skeletal equation without the unbalanced chemical equation, that you have to write first, obviously. And then the next thing is that you have to identify the oxidant and the reductant. right? Oxidant means the thing which is undergoing oxidation. Reductant means the species undergoes reduction, which is undergoing oxidation, which is undergoing reduction. That you first identify. Okay, now you'll be able to easily identify, checking for the oxidation numbers, whether it's decreasing or increasing for a particular element. You'll be able to easily decide whether it's undergoing oxidation or reduction. Okay, right. Then what you're going to do is you write the oxidation reaction separately, oxidation reaction separately, and then the reduction reaction separately. Okay, write it separately. Like I'll give you examples. Don't be just for now, just under the rules, right? So you're going to write the oxidation. You have to identify whichever is getting oxidized. Take that alone, write separately. Take whichever is undergoing reduction, write that separately in a reaction, right? And obviously, you have to include this with the removal. Say, for example, I know for undergoing oxidation, I would have removed some electrons. Those also has to be specified, right? The number of electrons lost or number of electrons gained in oxidation and reduction should be specified in the half reactions. Now, that's what when I write separately oxidation reaction, reduction reaction, those are what are called as half reactions, just like half cell. In one half cell oxidation, in another half cell reduction, like in electrochemistry, just like that. Right? Okay. Now you will write it along with the number of electrons lost or gained. Right? Again, electrons per formula unit. Be very careful. I told you in case of CR207 how you have to do it. Okay, anyways, we'll take some examples. Don't worry. Okay, so next, after identifying the oxidation reduction, writing the reaction, writing the half reaction along with the number of electrons, make sure now what you're going to do, you are going to make sure that the number of electrons lost is equal to number of electrons lost is equal to number of electrons gained. Right, number of electrons lost is equal to number of electrons gained. How you're going to make it? By suitably multiplying with the factor. For example, if say during oxidation I have lost 2 electrons and during reduction I have gained 3 electrons. Now I have to make sure that the number of electrons lost and gained are equal. So I'll multiply the oxidation reaction by 3, multiply the reduction reaction by 6. Sorry, 2. So make sure that the number of electrons lost and gained are same. Then now if you add the reactions, now the electrons will get cancelled. And obviously the stoichiometric coefficient now would have come because you would have multiplied throughout the reaction. Through both the half reactions, you would have multiplied. Okay, now that's not the step. That is not going to be the end of the thing, right? Even after this, what you have to look for is charge balance, right? You have to look for charge balance. Charge balance means whatever is the amount of charge on the reactant side, that should be the amount of charge in the product side. If not, you are going to make it equal. Right now, how are you going to make it equal? That depends on what kind of medium the reaction, what kind of medium the reaction is happening. Okay, so obviously you can have only 2 choices, right? Neutral medium, if they give you, you cannot do anything about it. If they give you neutral medium, eventually, like say after this step itself, the reaction will have charge balance would have been taken care right after this step if it's neutral medium, right? But if it is not going to be neutral medium, whether it's going to be acidic medium or basic medium, then generally the charge will not be same on both sides and you are going to make it equal. Okay, fine. So in this I can say that there are going to be 2 cases when I have say acidic medium or basic medium, right? Now what are you going to do, right? When you're going to have acidic medium, right? When you're going to have acidic medium, you are going to make sure that for charge balance, you are going to add H plus on the appropriate side, not like reactant side or product side. Wherever it is required, you add it. There is no restriction that it is going to be only in reactant side. On the appropriate side, right? Now, till now, whatever you have done, you wouldn't have actually touched about the oxygen atoms or hydrogen atoms. Actually, that's the first step, right? You really till this step, you even if you find that the oxygen atoms and hydrogen atoms are not balanced, do not worry about it. You are going to take care of that in this particular step. Okay, fine. So you are going to add H plus on the appropriate side, right? Now for adding for obviously for balancing the number of H plus, right? You are going to add water molecule on the opposite side. I don't know again which side, whether it's reactant side or product side. But for example, say if you would have added some 8H plus, I was just giving a random number, 8H plus on the reactant side, then to what to say, to balance the number of hydrogen atoms, you add 4H2O on the product side. Hope you get my point. 8 and 8 hydrogen should get satisfied, right? And sometimes even after you do this, the oxygen atoms wouldn't have gotten balanced. And do not worry about it. Okay, do not worry about it. There is some, because most of the time you will be given only ionic equations, right? You really don't know what is the cation, or sometimes you don't know what is the anion. Okay, now that would have eventually taken care. Okay, now sometimes, for example, if you go for this what is that, basic medium, maybe you will see that the oxygen atoms are not getting balanced, or maybe even sometimes the hydrogen atoms are not getting balanced. But as long as you have done everything properly here, and you are doing the charge balance properly, you do not have to worry about the hydrogens and oxygens. But 90% of times they will get satisfied. The number of hydrogen atoms and oxygen on the reactant side will be equal to that of the in the product side, right? So anyways, now same thing you will do for when you have basic medium. You will add how many number of OH minus you require for the charge balance on the appropriate side, and add water on the opposite side, right? Now in this case, it is going to be based on oxygen atom. For example, you have added 4 OH minus. Okay, you would have added 4 OH minus on the reactant side, then you go for 4 water molecules on the product side, because now it's going to be in terms of oxygen. Last time when it was acidic medium, it was in terms of what is that, H plus ion, that is hydrogen atoms, right? Okay, so these are all the steps, right? Now we will take some pretty good examples, and then we will move forward.
So for
Okay,
charge balancing, if it's an acidic medium, you have to add H plus
and
and
H2O.
yeah, and H2O, and if it's a basic medium, OH minus and H2O.
Yeah, correct.
Yes, sir. Okay, sir.
Okay, right. So anyways, we'll do some questions, don't worry. Fine. Okay, now what question? Okay, the same thing, next question. So MnO4 minus plus Fe2 plus gives Mn2 plus Fe3. Now I'm not going to give you, I'm going to tell you what medium is it, but you are going to tell me what medium is this.
Acidic.
What medium? How did you tell that?
Effective charge, sir. Left side it was +1. Right side it had +5. So I assume that H plus was somewhere added.
Same. I can even add. I can add more negative charge to that. Maybe more negative charge to that side so that it becomes equal. It's not based on that.
Oh, sir, oxidation state of manganese, sir.
Okay.
In MnO4 minus.
MnO4 minus, whether it's going to be acidic or basic or neutral, it's going to be +7 only. Yesterday only discussed, right? So remember, whenever it's an acidic medium, the product, the reduced species of MnO4 minus will be Mn2 plus. If it is going to be in basic medium, then it is going to be MnO2. If it is going to be neutral medium, then it is going to be MnO4 minus, right? But anyways, this is the balancing question. So they will give you what medium is it. But even if they don't give, looking at what is there in the manganese, the product side, you will be able to predict whether it's going to be acidic or basic or neutral. Now, in this case, definitely it's going to be acidic medium. Okay, right, fine. So let us go for solving this, right? So now we'll just write the oxidation numbers first, and first try to identify which is getting oxidized, which is getting reduced, right? Fine. So MnO4 minus, it's manganese is +7, and do not worry about oxygen atoms. Do not worry about it, except when you have peroxides, right? Hydrogen peroxide will only be the example. Do not worry. Okay. So it's +7 here, +2 here, right? And for iron, it is +2 here, +3 here. Okay, right. Now you see, obviously the manganese is undergoing reduction. MnO4 minus is undergoing reduction, right? And how many? Okay, now I'll not write it. Right. So first I'll see what is happening. MnO4 minus is becoming Mn2 plus. Now plus 7 to plus 2, obviously this would have accepted 5 electrons. Okay, this would have accepted 5 electrons to form Mn2 plus. Okay, fine. Now Fe2 plus would have become Fe3 plus by losing 1 electron. Right, now what is the next step? I have to make sure that the number of electrons lost and the number of electrons gained are going to be equal. Right, okay, so obviously the only way I can do this is if I multiply this reaction by 5, the number of electrons will be 5, then they will cancel when I add both. Right, okay, so now if you add them both, you will have MnO4 minus how many? 5 Fe2 plus gives 5 Fe3 plus plus Mn2 plus. No issues. Okay, whatever I told you, that's exactly what I've done. Right, okay, now what is the next step? I'm going to go for charge balance. Now it's given that it is going to be an acidic medium. Right, so let me calculate the total charge on this side. Okay, so total charge here is -1. Right, for MnO4 minus it's -1 plus I have Fe2 plus, so that's +2, but I have 5 such Fe2 plus, so it is going to be +10 plus 5, 5 into +2 will become 10. So what is the total charge here? Total charge is 9. Okay, now let me calculate here how much is coming. Right, so here I have 5 into +3 will become +15 plus there is one Mn2 plus which is going to have +2, so the total charge is 17 plus 17. Right, here it is +9. Right, now they have given it is to be an acidic medium. Right, so you can add only positive charge. Right, now this side it is more positive, this side is less positive, so obviously this side only I have to add H plus, so that the amount of positive charge increases and it becomes equal to +17, and accordingly I have to add the number of H plus. Okay, right, so now to make it equal, can I say if I add +8 to this, it is going to become +17. Right, so now in this case obviously I have to add 8 H plus ions to the reactant side, and for compensating that you go for adding water molecules, as many number of water molecules as required to satisfy hydrogen. Right, now there are 8 H plus here, so obviously I have to add 4 H2O on the product side. Right, now this particular thing what you have here is what is the balanced equation of this particular reaction, redox reaction. Okay, same thing, write the half reactions along with the number of electrons, make sure the number of electrons lost and gained are same by isotope multiplying, then go for charge balance. Right, by making sure that you're adding your either H plus or the OH minus based on whether it's going to be acidic or basic medium, and obviously in the opposite side add the water molecules to satisfy hydrogen or oxygen. That's it, as simple as that. Okay, we'll take one more example. Okay. Right, say I have MnO4 minus plus C2O4 2 minus gives MnO okay, gives MnO, and this is going to be what medium? This is neutral medium. Okay, so you don't have to add anything. Fine. So no, we'll keep it as acidic medium. Okay, we'll keep it as a zinc medium. So this is MnO4 minus plus C2O4 2 minus. Okay, right? This is going to happen in acidic medium, right? Okay, so now C2O4 2 minus is what is my oxalate ion, oxalic acid. Hope you remember, oxalic acid is this. This is what is oxalic acid, 2 COOHs, right? So anyways, so if I just remove the 2H plus, it is going to become C2O4 2 minus. Okay, fine. So you try to balance it. I'll give you maybe 2 minutes, quick.
Sir,
Yeah.
22H plus 2 MnO4 minus plus 10 C2O4 2 minus gives 2 MnO plus 10 CO2 plus 11 H2.
Okay, some things were correct, some things were wrong. Okay, let me check. Right, fine. So again, we'll go for the half reactions. So you can easily see MnO4 minus became MnO. So here it is +7, here it is +2. You can easily calculate if you want, right? Then you see C2O4 2 minus becoming CO2. C2O4 2 minus, what will be the charge? 2x minus 8 equal to -2 plus 3. Right, here +3, here it is +4. Right, so obviously this is oxidation, this is reduction. Right, now here you can easily say that I have to accept oh, this is plus, am I doing it correct? Okay, fine, this is correct. So +2, basically it's going to be 5 electrons. Okay, addition of 5 electrons I have to do. Now for this you see that +1 to +4 is 1 electron. Basically 1 electron should have been lost, but that is for 1 carbon atom, right? So when the first thing you will do whenever you write the half reactions, leave about oxygen and hydrogen. But other than that, in here itself, if we find that there is something missing, say for example, here there are 2 carbon atoms, here there's only 1 carbon atom, first put 2 here. The same thing what you do for chromium dichromate. Cr2O7 2 minus will give me Cr plus 3. But when you write the half reaction, you will write Cr2O7 2 minus gives 2 Cr3 plus. That adjustment has to be made here itself. Right? Okay. So what you understand is for 1 C plus 3 to become 1 C plus 4, there is 1 electron. But I know there are going to be 2 such carbon atoms going from +3 to +4. So it is not going to be 1 electron. It is going to be 2 electrons. Be very careful. Okay, right. Now all the steps are going to be pretty simple. Now we obviously have to make sure the number of electrons lost in it are same. So this definitely has to be multiplied by 2, and this has to be multiplied by 5. So the 10 electrons will get cancelled. Then you have to add it, right? So now when you do that, okay, when you do that, you will get 2 MnO4 minus plus 5 C2O4 2 minus gives 2 MnO plus 10 CO2. Okay, right? So this is the this is okay. This is MnO4 minus. Okay, So this is the the charge balance alone has to be done. Right. Okay. So let me calculate the total charge on the reactant side and product side. So here it is 2 into minus 1. 2 into minus 1 is minus 1. 5 into minus 2 will become minus 10. Right. So it's minus 11. Right. And here it is 0. There is no charge. Okay. So I think I have. So they are given it's going to be acidic medium. Right. So definitely I have to add 11 H plus. But if I add 11 H plus, how will I add water molecule?
Sir, add 11 by 2 and then multiply it by 2, sir.
Maybe that will work. Yeah, right. Yeah. So if I just add maybe 11 by 2 H2O, sorry, H plus.
No, sir, 11 H plus and then
Understood.
right. Yes, sir.
On the right, I put 11 by 2 H2. Right. Then if you want, you can multiply the entire reaction by 2 so that everything will become proper integrals, not integrals, integers. Okay, done. I think what you told was correct. This thing. Maybe here I just tweaked the equation a little bit. That's why maybe I couldn't see it. But yeah,
No,
what
sir,
you
no,
told was
sir.
correct.
I made a mistake in that. C2O4, 2 minus.
Oh, here. Okay, understood. Fine. Anyways, so this is how you balance this equation. Now I'm going to take one more reaction. I'm going to take a disproportionation or contraproportionation reaction. Right. So please understand, disproportionation and contraproportionations are opposite reactions. Right. In both these things, one thing is common. Well, the thing which is common is there is going to be one element which will undergo oxidation, the same element which will undergo reduction. Okay. Now, if you want to give me, if I want to give you an example, right? If I want to give you an example, H2O2 will give me H2O plus O2. Right. Now, if you hydrogen, there's not going to be any change, but oxygen, I'm going to have some changes. Right. So here I know it's a peroxide, so it is -1. Right. Here it's a normal oxide, so for this oxygen it's -2, and for this it's 0. Right. So you see -1 to 0 oxidation, right? -1 to -2 reduction. So same oxygen, one element only, but that undergoes oxidation and reduction simultaneously. Right. So this particular reaction is what is called as a disproportionation reaction. Right. And if I write the opposite reaction, H2O plus O2 giving H2O2, then that would be my contraproportionation. But so the thing common is only one element will undergo oxidation and the same element will undergo reduction. Okay, fine. So we'll take a disproportionation reaction and we'll try to balance that particular equation. Okay, right? So that would be, okay, I'll take this example. Cl2 gives, okay, now they have given it like this itself. Cl2 plus OH minus gives Cl minus plus ClO3 plus H2. Okay, now this reaction is given to you and we have to balance it. Right. Now again, you don't have to worry about OH minus and H2O. We will include in the last time and we'll see charge balance, how is it going to happen, and accordingly we'll add if at all we want something. And it's given that it is going to be in basic medium, obviously, because they have already mentioned it is going to be, and they have mentioned OH minus the reaction side. Right. Okay. Now same thing you are going to do. Right. So let me just little help you, because you might get confused how to write the half reactions. Do not worry, just write it. I have Cl2 to become Cl minus. That's the first reaction. Cl2 to become Cl minus. What now before even doing anything regarding the electrons, what I have to do here? Tell me.
Balance problem.
Yes. Here I have to put a 2. Okay. Then you do whatever you want. Right. Okay. Fine. So now obviously here it is 0. Now here it is -1, and here you can see it's going to be +5 for this chlorine if you calculate. Okay, right. So okay, how many electrons? Cl2 to -1, it is 1 electron gain. That is for 1 chlorine atom. But how many chlorine atoms are there? 2 chlorine atoms are there. So you should write it like Cl2 plus 2 electrons will give me 2 Cl. Done. Right. The next half reaction, Cl2 becomes ClO3. Right, minus. Again, two chlorine atom will not help. Put two chlorine atoms here. Right. Now you see here it is 0 to +5. That is for one chlorine atom. So for one chlorine atom, 5 electrons lost. For two chlorine atom is definitely going to be 10 electrons. Okay. Then only thing you have to do is make sure that the number of electrons lost and gained are equal. So the easiest way you can do is multiply this by 5. Right, and you add the reaction. Right, when you add it, so there is going to be 5 Cl2 coming from this, and there is already 1 Cl2 here. So totally it will become 6 Cl2. Okay, 5 plus this, 5 from this, 1 from this, it will become 6. Right, then I will have 10 Cl minus, right, plus 2 ClO3. Okay, right, and obviously other than that I had 1 OH minus in the reactant side, 6 Cl2 plus OH minus, and here I have to put a H2O. Okay, right, now I have to go for charge balance. Right, now let me see how much is the charge here. Here I have -1, there is only one OH minus, and here I have -10 for this, plus 2 into -1 will become -2, totally -12 I have on the product side. -12 on the product side. Okay, and I have -1 here, -12 here, so obviously I have to add more amount of negative charge. So now I can directly put it as 12 OH minus. That's it. Okay, accordingly, you have to put the hydrogen atoms also, oxygen atoms also. So you have 12 oxygens. Here you have already 6 plus 1. Okay, here already have 6. So can I say here I have to put 6 more? Okay, so 2 into 3 will become 6. 6 plus 6 will become 12, and 12 oxygens. That's it. Okay, done. This is the maybe can I reduce it further? Yes, if I divide the entire reaction by 2, maybe you'll be able to reduce it further also. It will become 3 Cl2 plus 6 OH minus plus gives 5 Cl minus plus ClO3 minus plus 3 H2O. That would have been a better answer. Okay, right. So whenever you are given a disproportionation or a contraproportionation, do not change anything. Just write the half reactions. Even though you're going to get the same thing on the reactant side or on the product side, doesn't matter. You do everything, add up, you will eventually end up in the balanced equation. Okay, right. So that is about your disproportionation or contraproportionation reactions. Right. Now there are only few more things left. One thing is about hardness of water. One second, let me check. Oh, it's not about hardness of water. It is okay. Fine. So there are 3 things. Maybe I'll just give you the definitions and formulas. Maybe we'll do little problems on that, but I don't think I have to do problem. Just know it. Okay, fine. I'll just let you that. So first one is volume strength, or it's volume strength of H2O2. Okay, volume strength of H2O2. Right. So first I will define you what exactly is this volume strength. Right. Please take on the definition of volume strength. Right. It is the volume of oxygen gas. It is the volume of oxygen gas measured at STP. It is the volume of oxygen gas measured at STP obtained from unit volume of a H2O2 solution. Okay, obtained from a unit volume of H2O2 solution. Right. So if you just go to the definition, people, I'll repeat it again. It is the volume of oxygen gas measured at STP obtained from 1 unit volume of H2O2 solution. Now, please understand the reaction goes like this. Just now we saw the reaction. Right. If you even balance it, it is going to become 1 by 2O2. Okay, fine. So this is a balanced equation. Right. So for example, if I tell you the volume strength of a H2O2 is some 20 vol H2O2 or something, some random value, right? 20 vol or 20 volume H2O2. That means what? That means if I had 1 liter of H2O2, right, I would have got 20 liters of oxygen from this reaction. That's what it means. Okay. For 1 liter of H2O2, how much oxygen, volume of oxygen gas I'm going to have. Right. Okay. Now, if at all I have to maybe okay. Yeah, there is nothing. There's no. I don't think they need to really worry about the problems here, but I can just give you the formulas, right? So if I want to write molarity, now this is also a concentration. This is a way of representing the concentration of H2O2. But if at all you want to represent it in terms of something we know, that is in terms of molarity or normality, something like that, there are calculations for this, but we are not going to the calculations. It's pretty easy. The molarity of H2O2 in terms of volume strength is volume strength divided by 11.2, and normality of H2O2 in terms of volume strength will be volume strength divided by 5.6. This alone you remember. Okay, molarity of H2, this is V is volume strength. Okay, right? Fine. So that's about it. See, even if the questions are going to come, it will be simple formula substitutes. Right? Simple formula substitutes. Okay, you don't have to worry about it. Right. Next.
Sir, this is molarity, right? Sir?
This is molarity, not molality. Capital M always represents molarity. R. Small
Okay,
m
sir.
only represents molality.
Yes, sir.
Okay. Right. Then percentage oleum. I'll tell you what do you mean by that. Some other concentration. Okay, if you've taken this down, maybe I can run this. Right. So next is percentage oleum. We have to know what is oleum first of all. Oleum is a mixture of H2SO4 plus SO3. This mixture is what is called as oleum. Okay. First, I'll give you the definition first. Or if I can do some calculations to you, that will be better. Okay, fine. So guys, if you look at basically, I told you that this mixture is what is called as oleum, right? Okay. Now, if at all I want to prepare H2SO4 from SO3, right? Generally, what I do is I add water to SO3 to form H2SO4. Okay. Now assume that I have some amount of oleum already present with me. Okay, I already have some amount of oleum present with me, right? To that oleum mixture, to that Yeah, sorry, I got a call. So anyways, to that oleum, which is already a mixture of these two substances, if we add water to that, right? If you add water to that, what will happen? Can I say more and more amount of SO3 will give some amount of H2SO4? Already some amount of H2SO4 is already present, isn't it? In the oleum mixture, already some amount of H2SO4 is present. Now, if you add some amount of water to this, right? So there'll be more amount of H2SO4 present. There'll be more amount of H2SO4 formed, right? Now, for example, I say that I have 100 grams of oleum, right? For example, I'm telling I have 100 grams of oleum. That is a mixture of H2SO4 and this thing, right? Now, by adding right, say if I add 18 grams of water to this, right? If I add 18 grams of water to this, right? Now, what will you get is 118 grams of H2SO4. Does it make any sense? Yes, it will make sense. Now, in this 100, I don't know. Some would have been H2SO4, some would have been SO3. The total is 100 grams, right? Now, if I add water to that, whatever is the amount of SO3 would have gotten converted to H2SO4, right? And obviously, if I say that 18 grams of water is required to convert all the SO3 into H2SO4, obviously, the total amount of H2SO4 now I'll have in the solution will be 118 grams. Is it not? Now, as I don't know whatever is the mixture, I don't know the proportion, I don't even need to know, right? I have 100 grams of oleum. If I had 18 grams of water, and if I will definitely get 118 grams of H2SO4. Now, see, it's not like every time I will get only 118, right? In this case, I'm getting 118, right? Now, this, for example, if I have to tell in terms of whatever the name, I'll tell you percentage oleum, I will call it as 118 percentage oleum. Okay, well, obviously, why do now generally we don't have percentages greater than 100, but what I'm looking at is already I have some H2SO4. The amount of H2SO4 is going to become more and more, and that's why you see that the percentages are going to be in more than 100, right? So what do you mean by this is that okay, what do you mean by this is if I had 100 grams of oleum, right, I would have gotten 118 grams of H2SO by adding some amount of water. Okay, by adding some amount of water. That's what you need to understand. Okay, fine. So anyways, this is you like questions coming from this are very, 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 very rare, but still knowing it is just for your safer side. Okay, right. So if I say 118 percentage of oleum, that means for 100 grams of oleum, I will be getting 118 grams of H2SO4. If I tell you 124 percentage oleum, that means for 100 grams of oleum, I would have gotten 124 grams of H2SO4. That's what it means. Okay, fine. And lastly, degree of hardness. It's a simple formula. So generally degree of hardness is written in terms of ppm, right? Or that, so directly it's going to be the ppm formula. It's going to be mass of CaCO3 or MgCO3. Like basically calcium salts and magnesium salts are the ones that's going to cause hardness to the salts, right? So mass of CaCO3 divided by or mass of MgCO3 divided by total mass of water into 10 to the power 6. That's it, right? That is the formula for degree of hardness, right? So only thing I have to know is degree of hardness is measured in terms of ppm. That's it, right? That's why I put 1 million 10 power 6. Okay, so yeah, that's about this chapter. What is the time? Oh, exactly 5:30. Wonderful, right? So we have completed Rock's reactions, right? So maybe I have completed all the 11 chapters, people, except for your S&P block, but I told you that we'll do later. So next class we'll be doing your organic, whatever the remaining organic will complete, and then we'll go for all the physical chemistry chapters in your 12th class: electrochemistry, chemical kinetic, solutions, solid state, surface chemistry. All these are there. Other than that, I have coordination compounds, metallurgy, and what else? Yeah, these two. Now obviously the S&P block, then and D and F block. D and F block I don't think I have to cover because coordination compounds mostly will cover it. Okay, fine. So these are things are left. Right. Thank you so much, people. Even though only 2 of you are there. Oh, now I have 4. Great. Right. Fine. So I don't know when you came. Right. Anyways, thank you so much, people. We'll meet tomorrow.
Sir, I have a small doubt, sir.
Yeah.
Sir, it's in electrochemistry, sir.
Tell me.
Sir, if they say a cell is formed with Al3 plus and Cu2 plus, sir.
Al3 plus and Cu2 plus. Okay.
How do you decide whether which is an anode and which is cathode, sir? Which undergoes
You need to know the reactivity. You need to know the reactivity. Basically, you will be able to tell the reactivity. If it is going to be aluminium and copper, aluminium is more reactive, or I would say aluminium is more electropositive. The more electropositive element always undergoes oxidation, and the less electropositive element always undergo reduction. That's how it is. So aluminium will undergo oxidation, copper will undergo reduction. That's how it is.
Oh, so oxidation means anode, sir.
Correct. Just remember this code. LAO, left anode oxidation.
Okay.
Okay. Right. So yeah, the more electropositive element will undergo oxidation, and that should be on the anode side. That is the left hand side.
Okay, sir. Thank you, sir.
Okay. Yeah. Cool. Thank you, people. We'll meet tomorrow.
Thank you, sir.
Yeah. Thank you.
Thank you, sir.
Thank you. Thank you.